Good afternoon, class. Today we're going to begin Chapter 4, talking about atoms and elements. As always, please have your periodic table and a calculator with you so you can work the problems along with me. Chapter 4. Elements are pure substances from which all other things are built. Everything in the universe is built from elements. Elements cannot be broken down into simpler substances while still retaining their own characteristics. We use chemical symbols to represent the names of the elements. A chemical symbol consists of 1, 2, or 3 letters. They always start with a capital letter. And if they have more than one letter, the second or third letters are always lowercase. This is because cobalt, capital C, capital C, little o, and the molecule carbon monoxide, capital C, capital O, are two completely different things with completely different properties. So be careful when you're writing out your symbols. Again, the first letter is capitalized, the second letter is not. The periodic table organizes the 118 elements that are currently known to us into groups with similar properties, and it places them in order of increasing atomic mass. Mass, remember, a unit of weight, right? So as they get bigger, you go across the periodic table. Groups contain elements with similar properties, which are placed in vertical columns. Periods are horizontal rows of elements, counted from top to the bottom of the table as periods 1 through 7. So again, periods go across, 2, 3, 4, and groups go down. Group 1, group 2, okay? Of all of the elements, 118 that we currently know of, 20 of them are essential for your well-being. 4 of those 20, oxygen, carbon, hydrogen, and nitrogen, make up 96% of our body mass, meaning you're mostly oxygen, carbon, hydrogen, and nitrogen. Most of the hydrogen and oxygen is found in your body as water, although some of it is oxygen gas in your blood. Water makes up 55 to 65% of your body mass, so quite a bit of you is water. Other elements, such as the macro minerals, calcium, phosphorus, potassium, chlorine, sulfur, sodium, and magnesium, are involved in other processes of your body, such as the formation of bones and teeth. You might remember your mother when you were a kid making sure you got your calcium from milk for strong bones and teeth. Maintenance of heart and blood vessels, muscle contraction, nerve impulses, and of course the acid-base balance of bodily fluids, and the regulation of cellular metabolism. On the periodic table, we have 3 types of elements: metals, which are located on the left, nonmetals on the right, and metalloids along the heavy zigzag line, which we will see on the next slide. You will notice we have something called alkali metals in group 1, alkaline earth metals in group 2. This short, fat part of the periodic table are our transition metals. Then we have in 7a or 17 the halogens, and in 18 the noble gases. Those are names you should know, you should be familiar with. For instance, if I ask you what is an alkali metal, you should be able to look at the periodic table, find group 1, and say, oh yes, alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. If I ask you what's an alkaline earth metal, you should be able to look at your periodic table, find group 2, and pick out the alkaline earth metals. If I ask you for a transition metal, you should be able to pick one out: a halogen or a noble gas. These are important. Okay, again, metals, except for hydrogen, which is a nonmetal, all of the rest of the metals are located on the left-hand side of the periodic table. All of these elements in blue are our metals. Metals have special properties. They tend to be shiny, ductile. Ductile is a word meaning that you can string them out into thin wires. You may also think of it as flexible or pliable, essentially not brittle. They also are great conductors of heat and electricity. All metals are solids except for mercury, which has the symbol Hg. Mercury is a liquid. All other metals are solid. Nonmetals, including hydrogen, are mostly found on the right-hand side of the periodic table, right? All these in yellow plus hydrogen. Metals have exactly the opposite properties of nonmetals, nonmetals have exactly the opposite properties of metals. They're located on the right-hand side of the periodic table. They tend to be dull, brittle, meaning you cannot string them out into wires, and they are poor conductors, but often good insulators, right? Good insulators, which is the opposite of a good conductor. They tend to have low densities and lower melting points. Metalloids are the special class of elements that fall somewhere in between the two. They tend to exhibit properties of both metals and nonmetals. They're better conductors than nonmetals, but not as good as metals. They're often used as semiconductors and insulators because you can often modify them to function as either. Atoms are the smallest particle of an element that retains the characteristics of that element. In Dalton's atomic theory, atoms are tiny, 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 tiny little particles of matter. They are of an element that are similar to each other, but different from those of other elements, meaning all atoms of carbon are similar to all other atoms of carbon, but different from atoms of boron, silicon, germanium, or any other element. Atoms of two or more different elements combine to form compounds, and we can rearrange them to form new combinations in a chemical reaction. During a chemical reaction, we never create or destroy atoms. All of the atoms that exist in the universe are all of the atoms that we have. We cannot create new atoms. Atoms have the following subatomic particles. They have protons, which have a positive charge, electrons with a negative charge, and neutral particles called neutrons. An atom is made up of a nucleus, which is located in the center of the atom. Inside the nucleus are all of your protons and your neutrons. Protons and neutrons make up most of the weight of an atom, and they are found in the center. Electrons are tiny little negative charges that occupy a large empty space around the nucleus. We typically say that electrons have such a small mass, we don't count them as part of the atom. Because the mass of subatomic particles is so small, we have a very special unit of mass that we call the atomic mass unit. One atomic mass unit has a mass that is equal to 1/12 the mass of the carbon-12 atom that contains 6 protons and 6 neutrons, or essentially approximately the weight of a proton or a neutron. One atomic mass unit is 1 Dalton in biology. Electrons, again, have such a small mass that we typically don't include them in the mass of an atom, meaning it takes roughly 1,800, right, 1,800 electrons to weigh the same amount as 1 proton. Since no atom has anywhere near 1,800 electrons, we tend to ignore them when looking at mass. All atoms of an element have the same number of protons and the same atomic number, meaning, for example, sodium, Na, all sodiums have an atomic number of 11. The atomic number is a whole number, never a decimal or a fraction. It's always a whole number. It is the same for all atoms of that element, and it is equal to the number of protons in that atom. This number can be found above the symbol of the element on the periodic table. Now, all atoms are neutral, meaning their net overall charge is 0. Therefore, the number of protons that they have must equal the number of electrons for an atom. So sodium has 11 protons. Therefore, an atom of sodium also has 11 electrons. Aluminum has 13 protons and therefore must have 13 electrons for its net overall charge to be 0. Let's use the periodic table to fill in the atomic number, number of protons, and number of electrons for each of the following elements. Nitrogen. Where is nitrogen on the periodic table? What kind of an element is it? Looking at our periodic table, we can see that nitrogen appears on the right-hand side of the periodic table. Therefore, nitrogen is a nonmetal. It is likely dull, and brittle. Its atomic number is 7. It has 7 protons. Because it is neutral, it also has 7 electrons. Zn is the element zinc. Where do we find zinc on the periodic table? Well, let's take a look. Zinc is on the left-hand side of the periodic table. Zinc is element number 30. Its atomic number is 30. Therefore, zinc has 30 protons and 30 electrons. Sulfur. Where is sulfur on the periodic table? Sulfur appears on the right-hand side of the periodic table. Its atomic number is 16. Because it's on the right-hand side of the periodic table, sulfur is a nonmetal. With an atomic number of 16, it has 16 protons and 16 electrons. Let's talk about the mass number. The mass number represents the total number of particles in the nucleus. Remember, in the nucleus, we have protons and neutrons. So the mass number is equal to the number of protons plus the number of neutrons. The mass number is always a whole number. Again, no fractions or decimal points. This number does not appear on the periodic table. Again, you cannot find the mass number on the periodic table. Example 2. An atom of lead, Pb, has a mass number of 207. We want to know how many protons are in the nucleus, how many neutrons are in the nucleus, and how many electrons are in the atom. Well, in order to determine how many protons are in the nucleus, we need to look at our periodic table and find the atomic number of lead. So let's take a look. Lead has an atomic number of 82. Lead is on the left-hand side of the periodic table. Lead is a metal. With an atomic number of 82, lead has 82 protons. How many neutrons are in the nucleus? Well, the mass number tells us the number of protons plus the number of neutrons. We know that the mass number is 207. We know that the number of protons is 82. So if we take 207 and subtract 82, we should find the number of protons. The number of protons is 125. 125 neutrons. Finally, we wish to know how many electrons are in the atom. Again, remember that an atom is a neutral species. Therefore, the number of protons and the number of electrons must be equal. Therefore, there are 82 electrons in one atom of lead. Now let's talk about an isotope. An isotope are atoms of the same element but have different mass numbers. All atoms of the same element have the same number of protons, right? All elements of the same atom all atoms of the same element, have the same number of protons, but they might have different numbers of neutrons. We can tell the difference by their atomic symbols. So, the symbol of an element includes the two-letter code, right? The two-letter code Mg. In this case, this tells us the particular element we're looking at is magnesium. The mass number, which tells us the number of particles in the nucleus, i.e. protons plus neutrons, and the atomic number, which tells us the number of protons, and in a neutral element, the number of electrons. So let's take a look at some examples here. We want to determine the number of protons, neutrons, and electrons. Let's look at oxygen. An isotope of oxygen has a mass number of 16 and an atomic number of 8. So atomic number 8, mass number 16. Remember that the atomic number tells you the number of protons. So therefore there are 8 protons in this isotope of oxygen. To determine the number of neutrons, we take the mass number and subtract the atomic number, because the mass number is the protons plus the neutrons. We subtract the number of protons to be left with the number of neutrons. 16 minus 8 tells us there are 8 neutrons. Let's look at another one. Phosphorus. Phosphorus has a mass number of 31, an atomic number of 15. How many protons does phosphorus have? Again, the atomic number tells us the number of protons. Therefore, there are 15 protons in one atom of phosphorus. The neutrons comes from the mass number minus the number of protons. 31 minus 15 tells us that there are 16 neutrons in an atom of phosphorus with the mass number 31. Let's look at an atom of zinc that has the mass number 65 and the atomic number 30. Mass number 65, atomic number 30. The number of protons comes from the atomic number, so the number of protons is 30. The number of neutrons comes from the mass number minus the number of protons. 65 minus 30 tells us that there are 35 neutrons. Let's look at another example. Naturally occurring carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. Let's look at the number of protons, neutrons, and electrons in each of the 3 isotopes. Carbon, looking at the periodic table, has an atomic number of 6. Therefore, all carbons have 6 protons, regardless of their mass number. All carbons have 6 protons. All carbons in a neutral state, all carbon atoms, also must then have 6 electrons, right? Since their number of protons and number of electrons must all be the same. Neutrons are the only thing that is different in an isotope. Carbon 12 has a mass of 12. The mass number is the number of protons plus the number of neutrons. So to determine the number of neutrons, let's take our mass number and subtract our number of protons. 12 minus 6 is 6. So for carbon 12, there are 6 protons, 6 neutrons, and 6 electrons. Now let's look at carbon 13. To determine the number of neutrons in carbon 13, we will take the mass of 13 and subtract the number of protons to determine that there are 7 neutrons. So carbon 13 has 6 protons, 7 neutrons, and 6 electrons. Why don't you try carbon 14? Carbon 14 has 14 protons and neutrons minus 6 protons, leaves us with 8 neutrons. Again, the only difference in an isotope of an element is the number of neutrons. The number of protons and electrons stays the same. This concludes Chapter 4, Part 1. Thank you for listening.